Hello everybody and welcome back to Chem Talk, where today we'll be talking about lattice energies. This is actually one of my favorite things that I learned in Gen Chem, and so I'm very passionate about this because I absolutely love lattice energy. Now let's get into this. So first question is, what is lattice energy? So lattice energy is a type of potential energy that adds to the stability of ionic solids, and it can be described in two separate ways. So it can either be the energy required to break apart an ionic solid and convert the atom in the compounds to their gaseous states. So if we're going according to this definition, our lattice energy value will always be positive. The second definition is the energy released from the gaseous state to form an ionic solid, and the value is always going to be negative. With this definition, our process is always going to be exothermic according to this definition. That means energy is released. So that is why our value is always going to be negative. With the other definition, that is going to be endothermic, so that is when energy is absorbed, and that is why our value is always going to be positive. Now, I have drawn, to the best of my ability, a sort of diagram of ionic compounds, and we're going to see that it alternates between positive and negative. So the positive are going to be green, and the negative are going to be purple. And so the interactions and the way that these atoms are held together, that stability is due to lattice energy. We're going to go into what lattice energy is composed of. Now, in order to actually see what lattice energy is, we're going to go over the Born-Haber cycle, which allows chemists to understand the stability of ionic compounds by finding the separate components of lattice energy. So we're going to be able to see, we're going to start off with a generic compound, AB2 solid. I know, very original. So we're going to go from the first step, we're going to do the heat of formation, which is bringing our A still in a solid, but we are going to be going, our B2 is going to be 1/2 because we only want one part. We only want half of our bonded together B, and that's going to be in the gas. The next energy that we're going to have is the heat of atomization, and that is when we're bringing our A into a gas. The next one is heat of dissociation, and that is when we are breaking apart our B elements. So B is actually naturally guessing that it's formed in 2. So because we only want one, we're going to have half of our heat of dissociation. The next one we're going to do is the ionization energy. So ionization energy is actually removing an electron from A. And then we're going to do our electron affinity, which is adding an electron to B. And then we're going to have lattice energy. So as you can see on the side over here, lattice energy is defined as our heat of formation subtracted by the total values of our heat of atomization, half of our heat of dissociation, our ionization energy, and our electron affinity. Now the next slide goes over the important terms that we should know, and I went over this a little bit, but we're going to go in a little bit of a depth in here too. So our heat of formation is basically the change of energy from when the atoms are formed to our compounds. So when our atoms are basically from singularities and then it's brought down into our compound. Our heat of atomization is the energy required to change the phase from a solid to a gas. So we see that from step 2 to step 3, we can see that our B component is actually brought from a gas to. So as we can see in the second step, we can see that our A component is brought from a solid to a gas. So that is the energy required to change the state of our component A. Our dissociation energy is the energy required to break different elements apart. So say we have a compound like chlorine, which always naturally forms in 2. So we have a chlorine attached to a chlorine. So we need only half of that compound. So this is the energy required to break apart our diatomic elements. And we're only going to need half because we only need half of our diatomic elements. The ionization energy, like I mentioned, earlier, is the amount of energy required to remove an electron from an atom. So we can see that A has an electron removed from it to give it a positive charge. And the electron affinity is the amount of energy released to add an electron to an atom. So we can see that B has an electron added, which is why it has a negative charge. And we can see that in order to go from our last step all the way down to a solid, that is the lattice energy, which is, like I said earlier, the addition of all of these components added in the way that is written in our formula earlier in the video. Now I'm going to do a very common example that is used when we're trying to look at the Born-Haber cycle, which is NaCl, which a lot of you should know is table salt. So, you know what we use to season our food and make it a little bit spicy. We are using that component and seeing how it is made and broken apart from gas to solid. So our first step is to draw out our Born-Haber cycle, and I am not the best at drawing arrows, so I've drawn them as neat as I possibly can. But this is basically the way that you should be seeing the Born-Haber cycle. It is called a cycle because it is continuously, when heat is being applied, it is continuously going from a solid to a gas, all the way being decomposed back to a solid, and it's going around and around and around in an equilibrium. So the first step should be the heat of formation. So it's going to be negative 411 kilojoules. And then the next one we're going to do is atomization. So that is bringing our sodium into a gas. That's going to be positive 108 kilojoules. The next one is going to be bringing our Cl2 into only 1. So we're going to need half of our value of the heat of dissociation. So that's going to be half of 244, which is going to be 122, as we're going to see in our equation later on. Then the next amount that we're going to need is the ionization energy, and that is to remove the furthest electron. So that's going to be the easiest electron that you can remove, and that's going to be 496 kilojoules, which is a lot of energy. So even removing one electron from here is very, very hard, even though it's in the outermost shell. The next energy we're going to go over is the electron affinity, and that is adding an electron to our chlorine, which if you're going to add an electron to your chlorine, because it is a halogen, it's actually going to make it in the electron configuration of a noble gas. So it's going to make it a little bit more stable. So we're going to be able to see that it actually releases 349 kilojoules. And now we have our heat of lattice. So now we have all of these values, and we want to see what the lattice energy equals. So we're going to use our equation that we defined earlier. So we're going to have our heat of formation, so negative 411, subtracted by all of the other definitions or all the other values added together. So 108 plus half of our heat of dissociation, which is 122, plus our 496 from our ionization energy, plus negative 349, which is our electron affinity. And we're going to be able to see that our lattice energy is negative 788 kilojoules. Now, if your professor, or if for any reason you want to convert this to joules, you would just have to multiply this number by 3. And just to make our lives a little bit easier, and because scientists are lazy, we're going to put it into our scientific notation. So in scientific notation, we're going to have 7.88 times 10 to the third joules. Now, why is lattice energy so important? And are there any real-life examples? No, in general, you're going to learn this in the classroom, and usually it's only seen in the classroom. It's a very archaic definition, and it's not very commonly used anymore. But if our scientists in the world want to find out how much energy it takes to break a compound apart, make it vaporize, and then bring it back down, just so we know the kind of boiling point, melting point, evaporation point, and everything like that, that is why we use lattice energy. So, for example, we're trying to make MgCl2. So MgCl2 is a compound that we use to de-ice roads. This is used very common in my area because our roads are icy 6 months out of the year. So in order to synthesize more of this compound, or in order to find out how to synthesize more of this compound, we're going to use lattice energy to see how much heat is needed for synthesis. And over here we're going to see a very interesting photo that I have drawn of snow falling, and we have our little shovel with our little truck driven by our very, very amazing people that run this whole facility. And we see that he is distributing this NaCl, or this salt that we have, that is going to de-ice our roads overnight so people can go to school and people can commute to work and everything like that.